All right, so I wanted to do a video of WebAssign problem number 4. So it was bounded from 3 root 2 to 6, and we had dt over t cubed times the square root of t squared minus 9. So there's something in the notes that I gave you from 5.7 that says if you have the form that is x squared minus a squared, then you should let x equal a secant theta. So that's kind of the form we're going to use. I'm going to go ahead and actually replace all my t's with x's, just because that's one less confusing point if we make everything start with x's. So we just got all x's. All right, so now we know that x is equal to, well, let's find out. Let's start with what is a. So a is 3. So x is equal to 3 secant theta. Then dx, meaning the derivative of x, would be 3 secant theta tan theta, d theta. I also have, notice I have an x squared in this integral, so I should have a representation for x squared. Well, that's just 3 secant theta squared, which is 9 secant squared theta. There's also an x cubed, so we should have a representation for that. 3 secant theta cubed, which is 27 secant cubed theta. Finally, I've got this whole representation in here of the square root of x squared minus 9. So that might be useful to represent that. And what does that look like? Well, I've got my x squared in there, which would be the square root of 9 secant squared theta, and then minus 9. I know I can factor out the 9, and I'm left with secant squared theta minus 1. I know that secant squared theta minus 1 is equal to tan squared theta. So I have the square root of 9 tan squared theta, and I can take the square root of each of these, and I would get 3 tan theta. So I do know that the square root of x squared minus 9 can be replaced here. So I've got all these different replacements that I'm going to be plugging in here. And let's see if I have everything. I have my dx represented here. I have my x cubed. I need to circle that. I have my x cubed, and then I have my square root of x squared minus 9 all there. So let's rewrite all of this now. There is one more thing. I'm going to have to deal with my bounds, because those were in terms of x, right? This is x equals 3 root 2 and x equals 6, but now I'm in terms of theta. So I'll need to change those bounds, but for now what I see is my dx can be replaced with 3 secant theta tan theta d theta. That's my dx in the numerator. In the denominator I have x cubed, which can be replaced with 27 secant cubed theta. And then I finally have the square root of x squared minus 9, which can be replaced with 3 tan theta. So I'm almost done, but I have to get those change of bounds. So that's one more thing I'm going to work on. Notice that there are going to be some things I'm going to cancel in this. So if I want to change my bounds, I have to define theta. So notice that, I'll rewrite it again. Since x is equal to 3 secant theta, then secant theta is equal to x over 3, and therefore theta is equal to the inverse secant of x over 3. But another way of writing that is I can just use the reciprocal of secant, which is cosine, and then the reciprocal of the values would be 3 over x. So now I'm finally at the place where I can plug in an x based on theta. So I have x equals, in this bound right here, I have x equals 3 root 2. So I'm going to say theta of 3 root 2, and that would be inverse cosine of 3 over 3 root 2. And you can see the 3's cancel. So I have that is equal to the inverse cosine of root 2 over 2, which I'm sure everybody knows is, I'll just put it here, pi over 4. So now I have to do the exact same to calculate the bounds for the upper bound, which was 6. So now I'm going to take the inverse cosine of 3 over x, but x is 6. Well, that's just the inverse cosine of a half. And again, you have to go back to your unit circle in case you've forgotten that. I'll just do it off to the side. So the inverse cosine of a half means I want the angle that gives me an x value of 1/2. And you can see that that's the tall angle, so that's the root 3 over 2. I'm sorry, not 3. I apologize, not root 3 over 2. Just pi over 3. Let's put that back, so that should be pi over 3. So my new bounds are from pi over 4 as the lower bound to pi over 3 as the upper bound. So I'm going to put those in pi over 4 to pi over 3. Okay, so let's look a little further. Notice that I can cancel this 3, this tan theta. In fact, one of the secants in the numerator with one of the secants in the denominator. So I am very close to being done. Let's just plug in everything that is rewritten now. So lower bound pi over 4 to upper bound pi over 3. In the numerator, all I've got is the d theta. I'm going to remove that 27 in the denominator as just a constant on the outside. So I have d theta over secant squared theta, but that is equivalent to, if I put it up in the numerator as cosine, so 1 over 27 pi over 4 to pi over 3, just cosine squared theta d theta. And now what I need is the rule that when the power of sine or cosine is even, we use the half angle formula. For that. And the half angle formula, just rewrite the whole thing now. We're going to go from, with 1 over 27 on the outside, pi over 4 to pi over 3, and then the half angle formula is 1/2 1 plus cosine 2 theta d theta. And now I can integrate all of this. So I have 1 over 27 on the outside, and actually let me take join the 1/2 times the 27 and just make that all 1 over 54 on the outside. And I'm integrating 1 becomes theta, integrating cosine 2 theta becomes 1/2 sine 2 theta, and I'm bounded between pi over 4 to pi over 3. This just gets messy math, but we're kind of done. So I'm going to leave the 1 over 54 on the outside, and then I'm going to plug in pi over 3 for theta, plus, if I plug in pi over 3 in for this theta, then I have sine 2 pi over 3. And sine 2 pi over 3 is here, and that would give me the value root 3 over 2. So I have the 1/2 times root 3 over 2, over 2. And then I'm going to subtract, and so now I need to plug in the pi over 4 into each. So I get pi over 4 plus, and then I plug in pi over 4 in here, and I get sine 2 times pi over 4, or sine pi over 2. And here's pi over 2. Sine of pi over 2 is just 1. I'll just put back here sine pi over 2 pi over 3 was root 3 over 2. Okay, so let me just finish this off. This is just, I lost track. Oh, 1/2 times 1, which is just 1/2. And so now it's just a matter of math. I combine the pi over 3 minus pi over 4, put those together. Root 3 over 2 times 1/2 is root 3 over 4, and I have minus 1/2. And finally, this becomes, if you combine them by a least common denominator of 12, it becomes 4 pi over 3 minus 4 pi over 12 minus 3 pi over 12 is 1 pi over 12. So I get 1 over 54 times pi over 12 plus root 3 over 4 minus 1/2. And that would be it.